Hi, in this lecture I want to give you all a description, a mathematical description of linear regression. Let's start with some data. So I'll call this column 1, column 2, and then the target column, okay? We're going to put in some values for these. So let's say 2, 3, and 6, -1, 0, and -2. For this one, let's go with 4, 11, and 17. And then imagine there are a lot of rows here. Okay, and I'll just put in maybe one more. How about 10, 9, and then let's go with 28. Okay, so here's the question. The question is simply this. Can we find a way to combine columns 1 and 2 to predict the target column, the third column? And, if you look at the first row, you might say, well, 2 times 3 is 6. Guys, multiply them together. Let's check. Well, -1 times 0 is 0. You get -2. That's not too bad, right? It's reasonable. It's not too far. 4 times 11 is 44. Maybe not. Okay. So we got to find another approach. It's not totally obvious just from looking at it. I mean, you could say, well, what if I double this column, right? 2 times -1 is -2, and do whatever with this column, because that'll give me -2. So if I do 2 times this column and 0, that's 4. Okay, so I don't know, maybe there's something we can do about doubling the first column. Now, linear regression is a mathematical model that does the following. It finds a multiplier of the first column, a multiplier of the second column. Guess what? If you got k columns, it's going to find k multipliers, and it's going to add them together after you multiply to try to get the target column. Okay? So let's consider a possibility for this one. What if we take 2 times the first column, okay? So these are going to be times 2. And then what should we combine that with as the second column? If you look at the bottoms in bigger number here, 20 plus, what can you do with 9 to get close to 28? Well, it seems like plus 1 of this column. So we can take 1 times this column. And note that you can certainly, what linear regression then does is it'll combine the columns. You can certainly have 0 times the column, negative number times the column, really any number times the column. Linear regression multiplies each of the columns by a number. Okay, these are often called weights in machine learning. You're weighting the column, and it simply sums them. Now in this case, we're going to get a particular error. Okay, let's see what we get. 2 times 2 is 4 plus 3 is 7, so we've overshot. So it would be like an error of -1. So we can consider an error here. Here we get spot on an error of 0. In this case, 8 plus 11 is 19. So it's too high, so we get, say, -2. And then, looks like we're always overshooting here. 29, too high, error of -1 again. Okay, but not bad. So this is a legitimate linear regression model. Okay, why? Because it's simply picking a multiplier of the first column plus a multiplier of the second column and add them up and see how close you get to the target. Now, if you start with random numbers, which is what linear regression really does, you're going to be off, right? You pick like, could pick like, what I actually use is sometimes it gets these random decimals. But it doesn't matter what you really start with. You start with 1 times the first column, plus start with one of each column and add them up, say. And then you do that and you get a bunch of errors. Okay, and it looks at the errors. Now, I want to pause before I get into the errors here, because I really want you to understand how linear regression works. It's actually kind of simple. Now, you may have seen, right, like you get these images where you can have dots, and you try to find, well, what's the line of least fit? And there's some line that goes through there, and maybe it's like this. okay? And the idea is that you're trying to minimize the distance between, say, the points in the line. Well, that's a geometric representation of linear regression. And it works well for 2 dimensions. It doesn't work well for actually higher dimensions. Here, our column space is 2-dimensional, but the whole space is 3-dimensional. Now, you can still do that visually, okay? What you end up with, if you can imagine, the points are like 3-dimensional, and so it's not a line of least fit, it's actually a hyperplane. So linear regression delivers hyperplanes in higher dimensions. But the visual representation gets lost once you have like even more columns of data. The method of linear regression, however, is the exact same, whether it's 2 dimensions, 3, or say in dimensions. Because, hey, if you got 15 columns, guess what? Linear regression is going to find 15 different multipliers. It's going to add them together to get as close as possible to the target. Now, this is hard for multiple reasons. One of them is that the target column could be all over the place. Okay, there might not be a good way to do it. Okay, the input space is what it is, right? The columns, those could be anything. You know, those don't, they need to be numbers here, but those aren't really affecting like, do I get a good result or not? It's all about how does the target column connect to them? Like in our example up here, there's no line of perfect fit, right? You can only get so close. And if I put even more dots up here, you know, both directions, you know, that line, maybe I need to add some more to keep it close to the line. But the line, you know, it's maybe not a linear relationship. It's not clear that there is a relationship there. So a linear model may not be the best fit, but this is how linear models work, okay? They're linear because they fit the form of, you're basically like multiplying and summing. But note that the multiplication here is times the column. I say that with emphasis because you're not multiplying columns together. You're actually finding numbers to multiply by the columns, okay? If I could try to write it out. I mean, here we have a line like y equals mx. And then, by the way, this plus b, so that's a standard straight line definition. The plus b is called like a bias term, and it's not as important as the m. The m, however, is importantly the multiplier, okay? Because that's what you're multiplying, you know, the target by. I'll just give you a simple example. I mean, if I'm to give you, say, like 2, 3, and 4 as your inputs, and I give you the outputs are 8, 12, and 15, well, if you do times 4, you get really close, right? The last one's a little off, but you would say that m equals 4. Why? Because in this case, we could, so this is like input and output, in and out, and then we could say y equals 4x, right? Because that's really close. So I found there's only one, all you got to find is one multiplier there, so it's not so bad. In this case, we've got to find 2. And so it's less important how to write it. It's more important to understand it, okay? So, you know, in effect, it's like, if you want to write it out in one way, it's like you could have m1 times x1 plus m2 times x2 plus another b, right? And that's what we have here. So in this particular case, we have 2 times the first column plus 1 times the second column. And then we can just assume too, we're going to keep our plus b of 0. Although in this case, you might want to do a plus b of, say, -1, because that's going to drop everything downward and would actually lower the error. But I don't, the reason why you don't need to mess with the b is because when you have a ton of data, it tends not to make as much of a difference. Okay, so we're just assuming in both cases maybe b is 0. And yeah, there's shorthand ways to write this, but again, the focus, say, at Berkeley Coding Academy and with a lot of my teaching is less on the mathematical formalism. It's more just getting the ideas down. So I know I keep emphasizing it, but I want you to try to get it. What is linear regression? Linear regression is all about finding the weights. In this case, it's 4. Now, what would it be in the picture? Well, if you picture the slope, okay, so slope is like rise over run. So it's like almost like if that's up 1, then it's over 2. So there, maybe it's 1/2. But in most cases in machine learning, it's not one column, it's many columns. And so you have a series of multipliers. But no matter how many multipliers you have, you're going to sum them all together. So if you have 10 columns, you need to find 10 multipliers and sum them all together. Now, how does the algorithm do this? How can it find, these numbers, right? I gave you kind of these pretty good, but hey, we could probably do better, right? It's a little hot, we're a little low, maybe it should be 1.1, right? Or 2.1, or let alone 2.1341. What about the missing data? Maybe the missing data will tell us, actually, those are a little off and they should be changed, okay? But the idea of machine learning is that the more data, the more the model can learn from the data to find the best weights. But as this picture shows, it's not necessarily the case that linear regression is going to give you perfect weights, because if the model is not linear, linear regression is not going to cut it, okay? But if it is kind of linear, meaning like, hey, there's general trends, it can get close. Okay, so let's move to phase 2 now. How does it actually do this? Well, it looks at the air, okay, and it says, how far off are we? Let me give you a visual here. Let's say that you have a function and it's a parabola, and this is the minimum error, okay? Right? I mean, if this is an error, okay, so here f is our error function. So it's plotting the error, okay? Then the lowest point is what we would call the minimum error. So that's our minimum error. Now, look, if you knew it was a parabola, then hey, you could be like, clearly just go to the bottom. But the reality is you have a point, you add up all the errors. And let's just take a little digression on that. Do you really add them up? Well, what if they were positive and negative? What if all the errors were -10 and +10, right? You say I have more rows here and I get a +1, +2, and +1. Do I have no error? Well, if you add them all up, you will get no error, which is why you don't just add them up. You take typically the distance formula, the square root of the squares, also known as the root mean squared error, but there are other statistical methods for computing the error. Okay, so there are different ways you can compute the error. But regardless, you have to have a way to compute the error, and then when you look at it, you say, how off am I? Okay, so let's say that you are up here, okay? Let's say you're there. What is that? What do you get out of that? Okay, it's the world of calculus, and the method is called gradient descent. And I'm not expecting that you know calculus, okay? Let me just give you an idea of how it works here. So this is a point, and what you do is calculus gives you the slope. It gives you the tangent line. The tangent line is where it hits the curve at only one and only one place. So it's hard to draw, but it's going to be something like that. The whole key isn't what's exactly the slope. It's that in this case, if you picture that line, that is a negative slope, okay? And if you have a negative slope, okay, you mean you have like a negative error, and you want to improve, what do you need to do? Go to the right, okay? Because, right, do you see that? What you want to go to that other dot. You want to arrive here. So you want to go to the right, okay? If I made that bigger, maybe there'd be some more clarity there. And this is what's happening under the hood. This is what the mathematics is actually doing, okay? So it randomizes the weights, picks random numbers, and boom, it computes the error. And it says, guess what? We got a negative. Go to the right. And then the learning rate, the step function, tells you how far to go to the right, okay? So let's just say we go to the right and you end up over here. Okay. Well, now when you look at the slope of this line, that's positive, right? That's positive slope. So that means go left, go negative, okay, go down. And so you go in the other direction. And so this is what it's doing. It's continually, over each iteration, getting the error and then making an adjustment using calculus, gradient descent in particular, based on that error, with the goal of getting as close as possible to that minimum, okay? It takes a step, a learning step. Like in our case, look, if I just look at, see, you're looking at a distance metric and it's like not quite this simple. But if you want to consider like the idea of, hey, this is like a negative error, maybe I have a negative slope here, then what we would do is we would modify the weights by like moving them up, right, going to the right. See how that works? So that's the general idea. Now, let me just see if I can summarize this to try to bring it home. What linear regression does, I mentioned this quite a few times, all right? This is the main takeaway from the video. It finds multipliers for every single input column. And it adds them together with the goal of getting as close as possible to this target column. Okay? First take, it randomly picks. It's not going to do well. It's got a big error. But the key is, where are you in the error? Is it like a negative gradient descent or is it positive? And then you step in the other direction. Okay? So it's going to make a step and it's going to adjust the weights. And like, I don't know, like actually how many iterations it goes through. Like, let's just say maybe like 100. Okay? So like how many times do you need to do to get a good model? Well, you do this thing 100 times. If you have the right step, you know, it's going to have their own steps by default. And other models, you know, you can pick your step. And, you know, you can imagine you're trying to get as close as possible. But as this example shows, you can't necessarily get zero error. So you could just end up going back and forth and get stuck between two numbers. But that is the method, and that's the mathematical method. So in my mind, when I think about linear regression, in terms of machine learning, I think of two things. I think number one, is the model linear, right? Here, no. Here, you know, I mean, maybe, right? And why do I say maybe? Because it appears that if I double the first column and add one to the second, I get pretty close, right? We're only looking at 4 data points here, so we would need to see how it does with all of them to really know. And that would be like a hyperplane. So an example would be like housing could potentially be linear because like you have the house price, but like, so more bedrooms mean houses go up. More like square feet, houses go up, right? And so typically you're like combining like good features and the cost of the house will go up. That's kind of like a linear relationship. As columns go up in value, then the target goes up, right? So that's it really, right? Is it linear? If so, linear regression can work. And the other piece is, how is it linear? Multiply and add. These are called weights. 2 columns, 2 weights. When I say 2 columns, I mean 2 columns in the, what do we call it? The predictor columns. Because you have 3 here, right? But we're not using the third. Okay, this third column, see, is not. It's the y. Y, okay? These are the x's. So this is x1, this is x2, and this is y. Just like in this one, the in, this is x. Okay, and this is y, the out. All right, so you've got an x and a y. And we have the equations here. So the question is, what do I multiply the x's by? Summing them, okay, to deliver the y. All right, so that is an introduction with emphasis of the same thing several times. Because honestly, you all, I know what it's like. I've actually been there as someone who has a strong mathematical background, and also like when I first learned linear regression and machine learning, it wasn't clear to me what it was. Like I had some of the ideas, but it wasn't like just clear how to put it together. And over time, like by asking questions, which is great that you all are doing, you're asking, yeah, but how does this work? And then looking for the answers and then thinking about it as well, you can start to make good progress toward kind of that understanding. And when you're building your models, do note this, as emphasized. If the model's not linear, you're not going to get a good fit. And I'll leave you with this too. In the real world, data is often not linear. It's often the case that there are better models that you can use to make predictions.